Okay, so in this video, I know there's a little bit of glare, I can't get this quite down. What we're going to look at, though, is we're going to look at the actual shapes using models now. So this is assuming in this video that you've already seen how to calculate the number of electron groups and how to count whether something is, how to deal with lone pairs and the idea of how that affects the difference in electron and molecular geometry. So let's take a look at those actual shapes now. So I'm going to start with the simplest structure, which is linear. This has two electron groups. So you'll notice you have a central atom here. It's got two bonding groups where it's then able to connect to these two atoms on the left and right. This is the furthest way to spread apart two electron groups. You'll notice they're exactly opposite each other, so this makes a line which makes this angle between these three atoms here 180 degrees. And that's because that's the furthest away you could get three objects. Note that if you had one of these that became a lone pair, like you took this off right here, and you just had two atoms, there was what's it called? An electron, a lone pair of electrons there, you're still going to get 180 between these things. Technically, it'll squish up, but if it tries to squish, it's going to squish in all directions. So even with just the one, if you try to take one of these off, you're still going to end up in that case. Note what I mean by take one of these off is, hey, cool, we have a representation. That's what it looks like with a lone pair. So it's not going to change shape for the two electron group case. Now, let's look at some more shapes. Our next shape stays in the same format that it's all in one plane. We get what's called trigonal planar. No, don't worry about the colors of the balls. I just picked the ones. These are just shape focused right now. So you have the central atom here, and the best way to divide this up is to put three things opposite of each other. Those three things being opposite of each other is exactly as far apart as possible. And since this is going to make between any of these sets of atoms, you're going to have a 120 degree angle. Because you've basically taken, if you imagine, you could draw a circle around this whole thing, and a circle is 360 degrees. So if you break the circle into three sections, that's going to be 120 each. So when you have trigonal planar, which is your three electron groups, then you're going to end up with a molecule that is 120 degrees with it. Now we'll look at the lone pairs later, please. I'm going to go through all the electron groups first before working at the molecular geometries. Let me see. That'll go there. Sorry, I'm just not quite enough, so I'm collecting some for my last shape. So our next shape is probably the one you'll encounter the most. This is because when you're working with molecules, a lot of things end up binding to four atoms because each bond represents two electrons, so you get 8 total and you've got a filled octet. So this is called the tetrahedral. It's the hardest I find to see on paper, but the idea is all of these angles, if you choose any three atoms, are 109.5 degrees. What's also neat about this is the way it's symmetric. Watch what happens when I flip it. Hey, there's one on top and there's three just barely below. Like if you look at this, it's just a little below. But if I flip to any one of them, hey, it does the same thing. One's on top, three's below. So if I think of this as like the z-axis here, I could think of these in the xy as they're slightly below the plane, right? So flat would be if it was even with my hand here, but it curves down a little bit. And that's where you get these angles to all be 109.5. And if you're rusty on the geometry, it's just hard to see, you can just believe me. Okay, Dr. Leslie said all the angles are 109.5. But this works, no matter how I flip it. And on paper, it can be hard to see that this really is completely symmetrical in the sense that any way I flip one thing along the z-axis, and technically the molecule doesn't have to sit there, we define the axes. The molecule can be like this, that's fine too. It's just harder to draw it, where it's like, oh, this thing's coming out at us, and this thing's coming at us, and this thing's coming back at me, and trying to get all that's harder, so we tend to orient one of them in the z-axis. That makes it easier to work with. Now that's 4 electron groups. Next we have 5 electron groups. So this is where we start having to have expanded octets. So we get this shape here. Note this is the only one that has 2 bond angles in it, because what happens is the best way to divide these 5 things up as far away as possible is to take your trigonal planar molecule. You'll notice here I've got 3 in this plane, and then I jam 2, one on top, one on bottom. I basically took a linear and a trigonal planar, and I bashed them together. And that's what I get. And so what happens is along this axis of what we call the equatorial atoms, equatorial being the ones that are like, if you think of this as the molecule, they're the 3 that are right here in the same plane. So we took this line where we define this as top and bottom of the z-axis, and then we put a trigonal planar molecule, so we put a triangle in between it. So for the ones in the triangle, those 3 atoms, it is a 120 degree angle. Then, for the axial atoms, that's what we call the top and bottom here. These are on the z-axis instead. These atoms, if we form the angle, now we're going to count the angle as the closest atom, so it's like this thing here. Those are 90 degree angles that we form. The reason for that is these 2 atoms attached to this middle atom made a 180 degree angle, but we split it in half with this triangle. So we have 90-degree angles and 120-degree angles, depending on if we're talking equatorial or axial. Again, equatorial is 120, axial is 90. Now let's look at one last shape, which I have to construct. I didn't have quite enough, so give me a second. Over here, the giant box of stuff. Note, some of these are different colors. Don't stress about that. This is my 6-electron group model, where they're all atoms, and this is octahedral. Now, this one I think looks, when you look at it look at this model thing, it doesn't always look octahedral. The idea behind it is if you take any 3 atoms, you can make a triangular face. So we make 1 triangle, 2 triangles, 3 triangles, 4 triangles, and I spin it around. And then on the bottom, it's symmetrical, you have those same 4 triangles. So it's 8 triangles if I take any of these 3 external atoms and look at the face it would make. So we end up with an octahedral structure. This leads to all 90-degree angles. The stuff in the axial position here is a square, and a square, we got 4 right angles between these. And then the top and bottom split, just like it was with trigonal bipyramidal. I hope I said trigonal bipyramidal earlier. If I said something else on n equals 5, it's supposed to be trigonal bipyramidal. I'm pretty sure I said something else. So we'll go over the shapes again just to make sure we're okay. So this is the octahedral shape. The other was trigonal bipyramidal. If I said trigonal pyramidal, that was wrong. And sorry for that. So yeah, so this is our octahedral shape. Now, all of the shapes I've shown you so far don't try to differentiate between a lone pair or an atom. All the figures I showed you just had atoms here, and so we call those the electron geometries. So in electron geometries, that's where the electrons are located at. In those cases, you don't care whether this is an atom or a lone pair, you get the same answer. But if you're interested in where the mass is at, then you want to know the molecular geometry. So all those things I showed you can be molecular geometries. If you have no lone pairs, the electron and molecular geometry are the same. But if you have lone pairs, it's different because there's no matter at the end of that. So now I'm going to show you all the shapes that are different when you have a lone pair. So they have different molecular geometry, but I'll go over what the electron geometry is again to make sure we're okay with it. So let's start with the first so I showed you the linear. That one didn't change at all because if you replace one as a lone pair, it's still a line. All the others change a bit. So we're going to start with the trigonal planar. I'm bad at these names too, right? So trigonal planar, this is what it looks like when you replace one of the ends with a lone pair. I left my lone pair on my bed. So we get this, where this thing here represents a lone pair. Sorry, I'm trying to keep the glare from being a problem. So what happens is rather than being a line, this lone pair takes up more space and it squishes these things together. So when it was trigonal planar, this would be 120 degrees. Instead, now it's going to be slightly less than 120. Note, it's going to depend on what atoms these are for exactly what it is, and I don't expect you to memorize that, but I would like you to know that this angle is a little bit smaller now because this lone pair takes up more space on the central atom. It's going to squish these things together. There's more electron density here. It's going to push these away to try to get away from it more. It wants more space here because it's not stretched out to another atom. So, if you have something that has 1 lone pair and 2 bonding atoms, that means you have 3 electron groups. So for electron geometry, this would still be trigonal planar. It's like there's 30 things here. But for the molecular geometry, because this here it doesn't have an atom on the end, we just call this bent. See, like you took a line and you bended it. So this is bent is the name we give this. And now you could put another electron group here. I can't think of a molecule that does that. There might not be. But in case there was, if you did, you put another one here, you just get a line because it'd be this atom here and this atom here. So we don't worry about those cases. Anytime you have 2 atoms, you have a line. It has to be. So let's look at some more shapes. Grab my lone pairs. There we are. So back to our tetrahedral shape. Woo, there we are. Remember, these are all 109.5 degree angles. Now remember, this is symmetric, so it doesn't matter where I put the lone pair. I'm going to put it in the z-axis first, though, because it's easier to see the shape then. So we're going to take this one, we're going to say, hey, instead of an atom, what would it do if we gave it a lone pair? So this lone pair is going to push all 3 of these down a little bit. I'm not going to break my model, so I can't show that. So they're all going to end up slightly less than 109.5. And in case you're worried about assessment things, literally we'll just have a less than sign, 109.5. It's not that you have to know, oh, this is 108 versus 107, or anything like that. We call this, and I think I mistakenly said earlier for a different shape, this is our trigonal pyramidal. So that's because we have this atom on top, and these atoms down here are still below it. So these 3, so this atom, and and this one over here, they're all three still in the same plane. So they form like the base of a pyramid, and then it goes up to this red atom here. And so that's like the top of the pyramid. Note, I understand that this shape, it actually is kind of harder to see than on paper because it's like, wait, that pyramid is really, really not very tall. And it's true. This is a really fat pyramid, the way it's made. Right? So the pyramid is really, really wide, and it goes up pretty quickly up to the top point. This doesn't have a lot of height. That's because of how these happen to be arranged. But this pushes it down. Now, in this case, this is one electron group, 3 bonding atoms. We can have a second electron group and only have 2 bonding atoms. Let's say I take this one off and put another one. Well, now we have 2. Notice that, hey, this is the easiest way to orient it. This is going to be less than 109.5, and specifically less than the one we just did. So as you have these lone pairs, they push the angle smaller and smaller. And hey, look, we got the bent shape again. So this is bent. It has the same name as the other one we looked at earlier with the 3 electron groups, at least for our text. Some texts will call this angular instead to make a difference, but we're just going to call it bent, and I'm fine if you call both shapes bent. But if you see the word angular, it's related to that, so some texts will do it differently. So don't let that stress you out, but yeah, it's bent, but it's bent at a different angle. It's less than 109.5 instead of less than 120. And again, you're not going to see a shape where you've got 3 electron groups here that I can think of, but if it was, you're just going to get a line because, again, you have 2 atoms. So yeah, atom here, atom here. So now, let's get to our last shapes. Of our more complicated ones. Well, not really more complicated, they just look bigger because there's a lot more atoms. Now we've got more planes. I mean, tetrahedral has 4 planes as well, or 3 planes as well. But this has got a little more. This is what's supposed to be trigonal bipyramidal, which I hope I said, and if I said trigonal pyramidal, I am so sorry. But it is trigonal bipyramidal. It has 5 total electron groups in it. This one is the only one you have to worry about this, but it matters which ones I take off first. It's going to be better to put electron groups in the equatorial plane. You're going to get a better shape. So that's what the molecule equalizes energy to be as low as possible. So the idea is it's just trying to spread all the electrons out as far as possible to keep them away from each other. That shape will do that the best. So I'm going to take one of these out and put a lone pair there. So now we have 4 bonding groups, and we have 1 lone pair, but still 5 total electron groups. So it's still the same electron geometry. But now, this shape's kind of weirdly named, but it's a seesaw. And this is where I do like the model for it. The idea is you take these 2 like the base of my seesaw, and look, hey, I can seesaw, yay. I didn't think it looked like a seesaw until I saw this. Like when I actually was just learning it the first time, I'm like, that doesn't look like a seesaw, Dr. Levitt. Dr. Levitt was my English professor, but it does. So I guess actually I saw that in high school. That was Mr. Ewan. But either way, it didn't look like a seesaw until I did this. I'm like, okay, I can seesaw that. Whee! I hope you remember me making this little motion at least. That'll help you remember seesaw. Because Dr. Leslie was a little ridiculous, and that's okay. Oh, angles. This is now less than 120. These are now less than 90 because this electron group pushes everything away. And again, I can't move it with this because it'll break the model. Let's put another one down. The next one also goes in the axial. Now we have 2 lone pairs and 3 bonding groups. Still 5 electron groups, 2 plus 3. But now we have an easier, much more logical shape. We have a T-shape. And you can rotate it like this to see it obvious, or you can do it like this. Oh no, yeah, this makes way more sense. So yeah, it's our T-shape. 1 in the equatorial, 2 in the axial. So we have a T. Here's a sideways T. Same idea though. Less than 120, less than 90. Oh yeah, just less than 90 because there aren't any atoms on this side. So just less than 90 here. This is why I like models. They help me my brain go, wait, there's not a less than 120 because there's not a spot for it. Now, we'll do one more. There's electron groups. Now you have 3 lone pairs and 2 bonding groups. And now, hey, we're back to a line. And because these are 2 opposite each other, just to be tricksy, not really, just what happens, it's now a 180-degree angle because these don't have any matter in them. So you don't have to worry about that. I mean, technically the electron has mass, but like it's not where most of the matter is. It's not an atom, and it's all stuck on the central atom anyway. It's not extended out to these other atoms like these are. So we now have linear again. So that goes through all the shapes for 5. Now we got one more to do. And that is our octahedral. So octahedral, remember, has 6 electron groups. And so when it's octahedral, that's just going to be 6 bonding groups. They all have angles of 90 degrees. Note that for this, unlike the trigonal bipyramidal, if I rotate this, there we go, my camera, as I rotate it, hey, it's all the same. We get the same octahedron. There's no difference in shape, so I don't actually have to worry about axial or equatorial. But we tend to, by definition, we tend to take them from the axial for naming the shapes. But as long as the two you take are opposite each other, that's fine. Like I could take this one here and this one over here, or I could take the top and bottom. But for naming the shapes, it's easier to do top and bottom. And they won't come from like here, and they come from over here. So they do have to come opposite each other as you add electron groups. So our first electron group, let's do the bottom. Makes it easier to name. We put this here. We now have a bunch of less than 90-degree angles. And because of this thing here, what we get is we get a square pyramid. Notice how these four are all in the same plane. So they make the base of a pyramid. And hey, they can all go up to this thing here. So we get a square pyramidal shape. And unlike our trigonal bipyramidal, this one looks like a pyramid closer because there's a bigger angle here. So it is a more standard pyramid, not quite such a fat, short pyramid. And we can make a second one here. Now we're actually back to 90-degree angles because these both push equally hard, so these are still 90-degree angles. And we get a square planar. Hey look, your 4 to the plane of square. So we have a square planar molecule here. And so that gets us through all our shapes. So hopefully that helps with getting an idea of them, and to help you remember your bond angles as well, and to have some sort of pictorial representation. What does Dr. Leslie mean when he says something like, this is a square planar? So hopefully that gives you an idea.